It's a pleasure to be today to talk to you about my work on the design of a type system for Elixir. This is as part of a PhD project that's done under the supervision and guidance of type system expert Giuseppe, Castagna, and José Valim himself. Let's just dive in and discuss why we want types in Elixir. Well, typing in Elixir, static typing, is meant to, first of all, catch a whole class of simple bugs, such as this function here that tries to do the Boolean negation of something that's always an integer, is going to give you a type error as such. For programmers, though, who don't put bugs in their programs, types are meant to be used as contracts that they put on their functions. For instance, sorry, there's a bit of a... All right. Just going to check in on that. For a simple function, such as negate, that works on integers, if we were to add a type system to Elixir, we'd like to add the possibility of writing those kind of type annotations. This is the type of functions that, when given a value of type integer, they return an integer. So now, if you use this function inside of another, such as subtract, well, the function type checks, because it checks that the plus operation is used on integer values. What happens, though, if... I'm sorry. What happens, though, if we modify the implementation of negate? If you add, for instance, a clause that's going to work on booleans, well, now you have to write a new type of annotation, and here's the kind of annotation that you may write. So this is the type of functions that, when given a value that is either an integer or a boolean, they return something that's either an integer or a boolean. And this keyword or here is a union type, and it is meant to be understood in its most intuitive meaning, that is, a value of type T1 or T2 is something that has either types. The issue, though, is now that subtract doesn't type check anymore. You get a type error, because the plus operator is used with something that may be a boolean, potentially, which is unfortunate, because if you look at this program, you know that, in fact, negate is going to be given an integer, and this function actually returns integers when given integers. So the issue here is a problem of precision of type. So you'd like to be able to give a type that captures this relation between input and output. And you're going to do that using a type intersection. So this is an intersection of two function types. And this type is the type of functions that, when given an integer, they return an integer. And when given a boolean, they return a boolean. And again, this has to be understood. This is a general type intersection operator, and it works on any type. And what it means is that a value of type T1 and T2 has both types. So now the subtract type checks, thanks to that. And this kind of expressivity, we believe, is key to allowing you to write annotations that are precise enough that you don't feel hampered by the type system. And you are able to statically type check programs that you're working on that or that you've already written. There's more to this. There are two features of this type system that are singleton and negation types, and that allow us to write precise types, for example, for this logical negation function. So this function tells you that when it receives an atom that is either false or nil, it returns true. So we can write a type that represents that, where here false is a singleton that represents its own value. So this type represents the first clause, and then the second clause tells you that when x is anything but the atoms false or nil, you return false. So we have this negation type, not false or nil, and this type represents any value that is not false or nil. The type system also includes polymorphism. So polymorphism is when a function can work on different types, and it's especially useful to write generic type annotations for functions, for libraries, such as the map function. And for that, we introduce type variables inside the syntax of types. So this annotation here, we have A and B, which are type variables, which can represent any possible type. And this is the type here of functions that when given a list of A elements, a function from A to B elements, it returns a list of B elements. And here, the type variables are quantified after the type using this when syntax, that is postfix, and we can put an upper bound on this. Here we wrote term, which is the top type, the type of any value. That means that A and B are not bound by anything, but we could want to put something smaller here, such as numbers or a custom type that you've defined. It's also possible as well to write more explicit name for those type variables. They are a tool for the programmer to write types that correspond to their programs. So you can replace A and B with element result or whatever feels best for you. The type system performs local type inference, meaning that if you write polymorphic type annotations, when those functions are used, the specific instantiation for those type variables will be deduced for you. So if you apply map to a list of pairs of integers and booleans, and the function that transforms such pairs into an integer, the compiler will know before compilation, right? Before running the program before compilation, that this application returns a list of integers. And we can mix all of this. So for instance, in this logical function, which takes 2 arguments, if we look at the first clause, it tells you that if the first argument is either false or nil, then you return the second one. So that means that you return exactly the type of the second argument, which is A. So you can write this type of notation. The second one tells you that if X is anything but the false or nil atoms, you return the type of this first argument. So you can write this second part of the type, B term to B. And here you can be even more precise, and you can put an upper bound on B, telling you that it can take any value beside not false or nil. And this is due to those negation types. They appear especially because of pattern matching. Because if you look at pattern matching, in terms of typing, the types that a first clause matches compared to a second one, they are going to be deduced from the possible types, the possible values that go past the second one. So it's really the natural way they appear. This type of notation again can be split, possibly on 2 lines and written with more explicit terms. And this is going to be equivalent to the previous signature that I wrote. Once we have this expressive type system, it's interesting to apply it to areas of the language. And protocols in Elixir are a good target for that. So just a reminder, protocols, they are a way to define a set of functions that we want to be defined for a given data type. For example, the string cast protocol asks that the toString function is defined. And currently, the Elixir compiler automatically assigns a type to all the values that, to all the data types that implement a given protocol. And it's called string cast T, or the name of the protocol.t. But right now, this term, it's an approximation, and it's a term approximation. But if we have precise union types, we can now construct the precise type of all data types that implement this protocol. And for string cast, it's going to be, well, the base ones, binaries, integers, list, and any custom types for which you've defined the toString function. This solves two interesting issues. The first one is parameterization of protocols. We can now express by enumerable T of A, where A is a type variable, the type of enumerables whose elements are of type A, which means that if you write a generic summation function that sums the integers inside of an enumerable, you can write this type of notation. Enumerable T of integer as a parameter returns an integer. What's also possible using set-theoretic types is the composition of protocols using an intersection. So if, let's say you have some data, some business data that you want to export, and you want this data to be exportable to JSON, CSV, and XML. And in Elixir, this means that they have to implement the JSON encoder protocol because it has the encode function, the CSV encoder, you get me. So you can define this custom type export and ask that it implements the three protocol. If you want the data to implement just one of them, you can use a union. This means that your value is going to be in one of those types. So it's good to have an expressive type systems, and ideally then at that point, programmers could just write perfect types for their programs, and everything is good. But in reality, we want the type information to be reflected towards the programmer as well, to provide some utility from programs that have already been written. And that is done. We can do that in Elixir because pattern matching is already very expressive in terms of the type information that it gives. So when I'm talking about pattern matching here, there's, of course, the case expression, but using the case expression in a function, it's equivalent to the usual definition of functions using multiple clauses with patterns in Elixir. So if we solve this problem of very precisely analyzing patterns and gods, we're going to have a wealth of information to exploit for typing functions themselves. And let's see what we can do. So if we have this type declaration of result, so this is the type of maps that have two fields. If the first field is the OK atom, then the second one is, the second field is socket, and it contains something of a custom type socket. If the first field is set to the error atom, then the second is going to be message with either the timeout atom or a pair of delay and an integer. Let's say you are handling this result with a pattern matching pattern, and what you're going to do in this function handle here, in the first clause, you match on the error output being OK. So you match the first part of the type, right? In the second one, you're going to match on error message being the timeout atom. By doing a type analysis here of the types the precise types matched by these two patterns, we can compare it with the type declaration and see that there's exactly one kind of values that are missing, and those are the maps with the error field and a delay and integer pair in the message field. So you're going to get a warning, a type warning here, that this pattern matching is non-exhaustive, and this warning tells you exactly what kind of values you're missing. We can do, conversely, the opposite. Let's say you've fixed the previous function, and now you have the first clause that matches on error output being OK, and the second one matches on it being error. And you've added a third clause, which aims at doing something with the socket field, but you know actually that this clause is never going to match. So you get a type warning as well here, that this branch is unused and should be removed. In fact, the patterns and guards give so much information that we can often guess the type, the return type, the precise return type of a function. So let's say here that you've written this code, and this type annotation here is a bit of a feature that if you want to just write the input type of a function and let the type checker guess the return type for you, you can write this underscore here. So in this function, if you go into it, the first clause is going to match on error output being OK. So at this point, we are going to narrow the types of the variables. Because they have succeeded some pattern matching operation, we now know that error socket at this point of the branch is something of type socket. So this branch here returns a pair of the accepted atom and a socket value. The second branch matches on error message being an atom. So it means that it must be the timeout atom. So error message in this branch is going to be timeout. And similarly, the only values that are left now in the third branch are maps with the error field and a pair here on the message. So that means that this is a pair and that its second element is an integer. So the third branch of this pattern matching returns a pair of retry and an integer. And the type checker is going to make the union of all the possible types for each branch and return it. And it is this union here. In fact, it's possible for it to be even more precise and infer a type that precisely captures the relation between input and output. And that would be this intersection type right here. So one key issue of the work was also the question of maps, which are very commonly used in Elixir. They used even for struct our maps underneath. And so we had to devise a type that captures all the possible uses. And here's what we come up with. So this is the syntax for defining a map, type of map T, which has one required field, foo, which gives you atom values. It has one optional field, bar. And if defined, then this should be an atom value. And then if any other atom field is defined, it's going to be an integer. And we can then type check the different map operations. So m.foo is going to be checked to have type atom. M.bar is going to give you a type error because the dot notation asks that a certain field is defined. There's another notation for map access, though, which is the bracket notation. So if you now try to do m bracket bar, here, because the field may be undefined, you get the type atom or nil. And then if you access any other atom field, you're going to get integer corresponding to other atoms, or nil. And in fact, because you can put any expression inside of the bracket notation, if you ask for any atom field, you're going to have the union of all the possible fields that go out of this map. And finally, if you try to query on something that's going to be an integer, you'll get type nil, because this field is never going to be defined, and possibly you could get a warning because of that reason you're trying to do a weird operation. So because no one has bothered to write type annotations for Elixir, because it hadn't been invented yet, if static typing is brought to Elixir, we'll have to go from zero typing in the way I showed you, to a lot of types potentially. And an idea that's been successful in, for example, TypeScript is to use gradual typing to achieve that. In our work, we would introduce the dynamic type to represent a type that can become any other type at runtime. And the question then is what kind of guarantee we give, because gradual typing can represent different things. In our case, we want to offer a type safety guarantee. That means that if your program has type integer and it evaluates to a value, then this value must be of type integer. You cannot have a conversion to something that's going to be a string through a dynamic conversion. And we achieve this. This is called sound gradual typing normally, but here we do it without modifying the compilation. That is, without inserting specific typecasts into the execution. And we do that by taking into account the type tests that are already being done in Elixir. And let me show you how we do it. So we do it by using strong function types. So what's a weak function type? Here is one. So we have this identity function that has type integer to integer, because when given an integer, it returns an integer. And it is weak because if you give it a value of type dynamic, you cannot say that it's going to return an integer, right? Because this could be a Boolean, and idweak is going then to return a Boolean. So here, the dynamic just erases your type annotations and renders them meaningless. However, you can see the difference with this second function, idStrong. This function has the strong function type integer to integer, because if you give it an input that is outside of its domain integer, it's going to error. So now you can say that idStrong apply to xDynamic as type integer. And this is what ensures a boundary, and being able to infer such strong types reduces the propagation of dynamic through programs. In fact, dynamic is going to be used as well to relax the way that the type checker type checks programs that you've already written. So let's say we haven't written any type annotation, that is function negate, then a type checker would infer that it returns integers or booleans. The issue, though, is that the function subtract, in dynamic mode, without any annotations, is going to give you a type error here, because you may potentially have a boolean inside of negate. And the way to mitigate that is that in dynamic mode, this return type is going to be intersected with the dynamic type. And this type, integer or Boolean and dynamic, it's a dynamic type that is bounded, that has to be within integer or Boolean. Which means that the type checker, when it sees A plus negate of B, it knows that plus is a strong type, that is a strong operator that checks if its inputs are integers. And it knows that integer or Boolean and dynamic can become an integer. So the type checking goes through, and this can be given type integer, or if you perhaps have singleton types for integer, it gives you integer or dynamic for more precision. And you still get benefit from this type of information that's passed around. Because if you try to do concatenation with negate, you get a type error, because those are incompatible types. So there's still a lot of work to do, and what we're on the short, medium term, what we're interested in is working on behaviors by trying to devise a type system with first-class modules that would give us something that corresponds to their use. There's currently work being done to add row polymorphism so that you can write type formats that are precise enough to type, for example, deletion operations. And the aspect of having complete type reconstruction for any program, and by using a technique called occurrence typing is also in the works. When it regards to typing processes, communications, or doing things like session types, those are ideas that are floating around, but that we're not working on at the moment. To do a little bit of recap, what we've been working on is formalizing a complete system for the language. We have a prototype that you can check online. It's the URL typex flydev. It's very experimental, and it's a few months old now. But if you want to try your programs and send me a bug because they aren't taken into account, there's a slight chance that it's a case I haven't considered. We have a paper that explains this general approach in a long written format, and you can check it. It's called the Design Principles of the Elixir type system. And finally, now we're working on the integration into the Elixir compiler, and so we're going to do that in a gradual way, going slowly, so that we do not introduce breaking changes for now, and just provide some nice, useful features in terms of types. Thank you for your attention, and I will take any questions.
Thanks so much, Guillaume. Questions? Yeah.
So as far as I understand, inference does not result in a unique type for an expression, but you can have, for example, a more broad union type or a more precise intersection type. How do you decide which kind of type you want to be inferred?
Mm-hmm. So it's true that because of subtyping, there's a series of different, more precise types that can be given to a function. How do we decide? Well, for instance, that's a good question. I don't think there's not a general answer there. The thing is that in this system, we plan to rely more on type annotations first, so that people write the kind of type they want their functions to have. And then inference comes as a guide to help guess a difficult type, or because the issue with doing full inference everywhere is that you can infer those very precise types, such as the one that I showed, this large intersection, and it quickly becomes a bit overwhelming, maybe. So the decision would be a trade-off between what's necessary for the type checker to function, and what the programmers need. But in terms of capabilities, there's a lot indeed you can do.
Thank you.
More questions over there?
Thanks for a great talk. It's really interesting, and you see that a lot of goodies are coming sooner or later. And my question is about, when exactly? Do you expect some time frame when the first developments are going to reach the Elixir compiler? Or maybe do you plan to offer preview versions of the compiler with some of these features available? I'm wondering about the plan around that.
That's a very good question, considering I'm probably the bottleneck on this. What's the plan, José?
We don't have a time frame per se, but our initial goal is to, because like adding the type system to the language can be a really large change, possibly the largest change the language could go through. So our initial work is to use the information that we get from patterns and guards and run that through your system and try to find obvious bugs. And the idea is that we want to implement like the core of the type system without you having to change any code, and find bugs in your code without you having to change anything. And this is going to be helpful because we can see if the type system is performing well, if the error messages are good, before we change the surface area of the language. So that's what we are working on right now, is making sure, allow the type system to get information from patterns and guards and start understanding more what your Elixir code is doing. And we are going to probably be at this step for quite some time, and then if it works out, we are going to do another step, and then probably like the third and fourth step is to actually change the language and allow you to specify the types like you see on the slides. So we did a blog post on the Elixir site that says exactly that we move from research into development, and there we outline kind of the plan, but no time frame.
Hi. So I wanted to ask if what about the compatibility with the existing type annotations, for example, for the ones who are using the Elixir or the Elixir?
My understanding is that the type specs and those annotations will coexist for a time, maybe forever. Those type annotations, they're going to be much more integrated into the tooling around Elixir. So there's going to be a real value to having those. And in terms of, those are different ways to do things. This type checker and the dialyzer, for instance. So you can potentially show that some things are similar, but at the end of the day, those won't be the same. This won't be the same typing discipline or the same algorithms. So it's not very compatible. José, yes.
Yeah, so they will coexist for a while, but I think if at a moment we say, okay, Elixir is typed and this is the official way of doing it, we are going to probably get everything that is related to dialyzer and put it as a package. And then if you want to use that, you use it as a package, but it will no longer be like a default part of the Elixir experience, because we don't want you to have to define types in 2 different ways. And the other thing that I think it's worth saying, some people ask, can you just get my type specs and convert them to the new types? And the answer is, like, we could, but we won't, because the type specs, they are not, usually we don't write them in a precise way. Like, so Guillaume gave an example where we wrote like integer or Boolean goes to integer or Boolean, and the more precise version is integer to integer and Boolean to Boolean, and the type precision aspect is important. And when we wrote all of our type specs that exist in our code bases, we were never thinking about this precision issue. So if all of this succeeds and we do get a type system, we want people to really think, oh, what is the proper type for this? And you have to convert the type spec. So of course, while we are still exploring, they will coexist. But my ideal version is that if this works out, then we no longer will have type specs as part of Elixir. It's a separate package that you can install if you still want to use them.
Yeah.
Yeah, so someone asked, like, the other way around would work. We could go from this type system to dialyzer, and I believe that's the case. We can convert, sometimes it may generate like very broad types, because if you say that something is not an integer, we will have to say that this is an atom or a string or a PID or a reference, but it can potentially work, yeah.
Just use term.
Yeah, may as well give up and say it's a term. Yeah.
Any final question? There's 2 more. Remember, you can also use the Vuva app afterwards to ask more questions. I'm going to run out of time here shortly.
You briefly mentioned tooling. Is there going to be any way to programmatically access these types or inferred types? So I'm thinking, like, right now you can get the abstract syntax tree and maybe manipulate that and then turn it back into code if you're developing tooling around refactoring. So will there be any way to sort of programmatically access these types for tooling purposes?
So you're asking if there will be something that goes further than like IDE tooling, where you get type warnings that help you work on your code. Sorry.
Yeah, reflection APIs. So I guess I'm thinking if you are a developer actually writing the tooling for IDE, you want to be able to reflect and maybe have access directly to what's been inferred.
Well, yeah, I think so. I do the type system, and then I think there's a lot of people who've given me good ideas that they will be able to implement once this goes out.
Thank you again very much, Guillaume. Again, please ask more questions, either via the Vuva app or talk to Guillaume. So thank you very much.
Thank you.